In one of the earlier videos, we saw how to normalize a dataset by shifting it so the mean becomes 0 and scaling it so the variance becomes 1. This process helps the data stay well scaled and balanced. Now, when the data is not normalized, the loss contours often look stretched and asymmetrical. In this case, the gradient descent or any other algorithm struggles. It takes long zigzag paths and updates become unstable. We have to be extremely careful with how we initialize our weights, and we are often forced to use a tiny learning rate to prevent the training from exploding. But once the data is normalized, those contours turn more circular and balanced. This lets the optimizer move smoothly towards the minimum, faster and with far more stability. This makes everything easier. We don't have to worry about choosing the exact right learning rate or starting values. Now imagine we have a deep neural network. Suppose the input data is already normalized, but as it travels through the layers, something interesting happens. The distribution of each layer's input keeps changing, layer by layer. This shifting distribution makes the network unstable and harder to train. In the original batch normalization paper, this problem was called internal covariate shift. The idea that each layer has to constantly adapt to the changing input distributions from the previous layers. Batch normalization was introduced to stabilize this internal covariate shift across the layers by keeping the inputs in a consistent, well-behaved range as they move deeper into the network. We will later see how this explanation is not fully accurate, and newer research has a better story. But for now, let's stick to this idea. So, our goal is simple. We want every layer to receive data that is already normalized, so the activations stay stable throughout the network. To do this, BatchNorm operates on each mini batch inside each layer. Suppose we have a mini batch X with m examples. The first step is to calculate the mean of this mini batch and then compute the variance of the same mini batch. Once we have these two statistics, we normalize this X. We subtract the mean and divide by the standard deviation. And we also add a small epsilon term in the denominator so that even if the variance becomes 0, we don't run into a division by 0 error. This centers the batch around 0 and keeps the variance at 1. We have actually covered this step in detail in an earlier video, and I will leave the link to that in the description. After normalizing, we scale these normalized values using a parameter called gamma, and then shift it using another parameter called beta. And these parameters are learned during training, just like the weights and biases of the network. If the network decides that normalization is actually bad for a specific layer, it can learn to set gamma equals to this denominator term and beta equal to the mean, effectively cancelling out normalization. This guarantees that the network is not forced to use the normalized data. It has the freedom to scale and shift it back if that works better. And by the way, this x hat value we have been talking about is simply the pre-activation, the weighted sum z of that particular layer. It's actually a topic of research about whether we should normalize the activations or the pre-activations. But in practice, most deep learning libraries apply batch normalization on the pre-activation z. Now, here is something interesting. The bias term in the layer becomes completely redundant when we use batch normalization. Let me show you why. Start with the normalization formula. We compute the mean of the pre-activations in the mini batch. Now, substitute the weighted sum. Now this batch summation over the bias becomes just B, and the summation over the activations, let's call it A bar, just for cleaner visuals. And once we substitute this mean back into the normalization formula, something neat happens. The bias term cancels out completely. And remember, we already have this parameter beta, which shifts the normalized distribution. So beta basically acts like the bias of the network. That's why the original bias term in the layer becomes unnecessary when batch normalization is used. Now, during training, we place the batch normalization layer right before the activation function. The weighted sum is computed first, then batch norm layer normalizes it, and only after that we pass it into the activation. This keeps the distribution of activations relatively stable across the layers as the network learns. Each layer now has parameters weights, gamma, and beta, and all of these are learned during training, just like the parameters in a normal neural network. Now, during testing, the process changes a little bit. To normalize the values, we need the mean and variance of the mini batch, right? But at test time, we may not even have a mini batch. Sometimes we just have a single input, and in that case, the mean becomes that same value and the variance becomes 0. That makes no sense for normalization. So instead, during training, batch norm keeps track of exponentially moving averages of the mean and variance. And during testing, we simply use these stored moving average values to normalize the data. So while training, we form mini batches for a particular layer and find the batch mean and the batch variance. Now, the goal is to maintain a moving average of these values. The formula for that looks like this. It's recursive in nature. And if we expand it out, you can clearly see that the older values fade away because they are multiplied by powers of the decay fraction repeatedly, while the most recent values stay strong. Using this, a running value for the mean and the variance is stored during training. And during testing, that stored value is simply plugged into the normalization equation. So that's how batch norm works. And if you read the original paper, which I highly recommend, you will clearly see that networks trained with batch norm learns much more efficiently than networks without it. And for a long time, it was believed that batch norm works because it fixes this thing called internal covariate shift, basically keeping the distributions stable at each layer. But later research showed that this is not the main reason why batch norm works. In the later research paper called How Does Batch Normalization Help Optimization? It was found that batch norm does not actually stabilize the distributions across layers in a significant way. In fact, in many cases, the distribution stays the same. So this clearly shows that fixing internal covariate shift is not the real reason why batch norm works. The more significant reasons are that it smoothens the loss landscape. The surface becomes less jagged, so small weight changes don't explode the loss. It lets us use much higher learning rates, which speeds up training a lot, and it often acts like a mild regularizer. The batch statistics introduce noise between batches, which reduces overfitting a lot. All of these together explain why batch norm helps so much, not the simple fix internal covariate shift story from the original paper. I would highly recommend reading both of these papers yourself if you really want to dive deeper into the theoretical side of batch norm. I will provide the links to both papers in the description.